All right, we're going to talk a little bit more about data analysis, and I would like to start with a story. Lion, fox, owl, gecko, and sloth meet up to talk about the books they've been reading. I just loved Perfecting Your Roar and Tofu in the Wild, A Vegan's Guide to the Savannah, shared Lion. That sounds great, said Fox. I read Sneaks by Catherine Egan and the first book in the Spy School series by Stuart Gibbs. I've read too many books to share them all, said Wide Owl, but I especially loved Who's There? A Guide to Bird Calls. Gecko licked his eye and said, I've read the entire Field Guide to Color, volumes 1 through 4. I just flew through a beginner's guide to speed reading, shared Sloth. All right, let's think about a couple of math questions we could ask about this situation. So one is, how many books did they read altogether? And the second is, assuming they still read the same total number of books, how many books would each animal have read if they all read the same number of books? I want you to see if you can come up with two different strategies for each of those prompts. So go ahead and pause the video, and then once you're ready and you've worked it out yourself, I'll share how I thought about these problems. All right, let's talk through about how I might solve these problems. For the first one, how many books did they read altogether? With a small data set like this, it's pretty straightforward. We could just count them if we want. Starting with 9, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 books total. However, if we had a lot more data points or our numbers were a lot larger, that wouldn't be very practical. And if we think about if we were to conduct a survey and ask people, how many books have you read? What we would be collecting from them would be the actual number. So we would have the numbers 2, 2, 6, 4, and 1. That would be our data set. And we could just add them up really easily and get a total of 15. So that's another way we could approach this. And again, if we had a really large data set, that'd be an easier way to do it. So then the next question is, how many books would each animal have read if they all read the same number of books? And again, the assumption here is that they still read the same total. And with a small data set like this again, kids might reason about this by sort of thinking about the individual books and how they'd move them around. So they might notice Owl has a lot of books, so maybe I'll take one of those, a couple books from Owl, and give one to each of Lion and Fox. And then I notice that Sloth is kind of low, so I'll take Owl and Gecko's extra books and give them to Sloth. And now I can see that if they had shared their books equally, they would all have read 3 books. However, again, let's go back. If we had a big data set, lots of numbers, or the numbers were really large, or maybe they didn't divide evenly like that, they didn't work out, then this would be a little tricky to do. So another thing we can do is we already know there were 15. We figured that out on the previous problem. And we know that we have to share them among 5 animals. And so we get that each animal would have read 3 if they had shared them equally. And this equation should look really familiar to you. It should remind you, or it should look like the equation you learned for calculating the mean or average in school. And this explains where that equation comes from and what it tells us. So this is one of the most powerful definitions of mean. This is what, when you think of mean or average, this is what I want it to evoke for you, is that the mean is a fair share. It tells us what each data point would be if the total had been shared equally among all the data points. And that's a really powerful way for thinking about mean, and it can help us solve problems. So let's do a first problem. You give a 10-point quiz to a group of 6 students. You figured out their average score was an 8, but then you lost one of their quizzes, so you don't know that student's score. You have the other 5 quizzes though, so you know the other 5 scores are 10, 6, 9, 7, and 6, and you need to figure out the missing score. So I'd like you to work on this problem. As you do, I want you to think about this definition of mean is fair share and think about how that can help you with this problem, as opposed to, say, sort of writing a formula and then calculating. If you want to write a formula as a second strategy and just sort of work through it, that's great. But I want you to see if you can start with this definition. So go ahead and pause the video, work the problem on your own, and then when you're ready, unpause, and I'll share how I thought about it. All right, so the first thing I'm going to pay attention to as I solve this problem is that the average score was an 8. And if I think of the mean as a fair share, that means the data could have looked like this if the average was evenly shared. Each kid could have scored an 8 on the quiz. And that means because there's 6 kids, I have a total of 48 points that they scored. But that's not what they actually scored, so I'm going to move those off to the side, and then I'm going to fill in what I do actually know. I know that the first kid scored a 10, so I've used up 10 of my points. I have 38 left. My next kid scored a 6. The next student scored a 9. The next one scored an 8. And the next one scored a 6. And so that tells me that I have 9 points left over for the missing score. And that helps me fill in the information. Formulaically, we're doing really the same thing, but I want to make sure we're grounding the meaning in the meaning of the mean. Sorry for the repeated usage there. So the formula we have, if we're just sort of thinking about it a little bit more algebraically, the formula we have is we add up all the data points, and K here stands for the unknown data point, the unknown score. We divide that by the 6 students, and we get an average of 8. We could multiply both sides by 6, and we would get this expression or equation. And again, I'm going to imagine my 48 points that the students have earned, and I'm going to think about how I can simplify this expression, or this equation, sorry, to find out what K is. I can subtract 10 and get 38 left. I can subtract 6. I can subtract 9. I can subtract 8. And I can subtract the last 6. And again, I'm left with 9. So it's really the same process. I just wanted to show algebraically what that looks like and what we're doing. And so that 9 is the number of points for that unknown students quiz. All right, let's work a second problem. I want you to imagine you have 4 different households. Their average income in 2021 was $71,000. And they all made somewhere between $55,000 and $90,000, and they all made a different amount. How much did each household make? There's more than one answer to this. There's many possible answers where they could average out to $71,000. So I want you to try to come up with 2 different answers to this problem. And as you're doing it, I want you to think about this definition of mean as fair share and how that can help you reason about the situation. So go ahead and work the problem, and then pause the video, then work the problem, and then unpause it when you're ready to hear my thinking. All right, so I would put my 4 households over here. The average income in 2021 was $71,000. So if I think of the mean as a fair share, I can imagine that they all made that much. So this household is going to make $10, $20, $30, $40, $50, $60, $70, $1,000. And I'm going to notate that as 71K just to save a little space on the screen here. And then I'm imagining that's true for all of them because that's the fair share definition of mean. And so altogether, they made $284,000. And that's a key piece of information I'm going to use. Now we want to keep in mind that they make between $55,000, so no one should make less than this red line, and $90,000, so no one should make more than that red line. And that's one strategy I'm going to use. I will just start with someone at 55 and someone at 90 and see how much money I have left to give out. That leaves me with $139,000 for the other 2 households. I can think of that kind of as $140,000, which I know I can make with 60 and 80. So I'll give this household $60,000, and then this household, not quite 80, it's 79 to get up to $139,000. And altogether, I have my total of $284,000 in income that year. Another strategy I would use is to just think of $55,000 as my minimum. I'm going to give that to everybody, so I'm going to start with that, and that leaves me with $64,000 left over. I have enough. I'm going to give everyone an extra $10,000. That leaves me with $24,000, and now I'm just going to sort of choose numbers and work my way up to 24, work my way down from 24. So I'll give this household an extra $5,000. They're at 70. That leaves me with 19. I'll give this household an extra 10, getting up to 75, and that leaves me with 9. And I'll give that 9 to this household, and that gives them up to 74. And so now I have 4 different values, and I have a total of $284,000. And so I know it will be the same average. I don't even need to calculate the average each time because I know as long as I'm getting up to $284,000, I'm fine. And that's part of how I'm using that definition. All right, so we've talked about mean as a fair share. Now I want to talk about a different definition of mean, which is where we think of the mean as a balance point. We're going to go back to our animal book club, and I'm going to push these data off in the corner so that we have them, but I want to represent them in a different way. I'm going to represent them in a dot plot. So I've got a number line here going from 0 to 7, and the number on the number line is the number of books read. So for instance, Lion read 2 books, so we'll represent Lion here. Fox will go here, Owl will go here, gecko read 4, and sloth read 1. Now, normally when we make a dot plot, we don't have little pictograms of our data, so I'm going to make it look more like a traditional dot plot where it's just dots plotted on a line. Right now, if we were thinking about what we want to think about with this definition of the mean is where's a balance point. We want to think of this as like a teeter-totter or a seesaw. And if I only had these two data points, 4 and 6, this would be a great balance point that would balance the seesaw in between them. But I have these other data points which would make the seesaw lean to the left here. So the question we're really asking is where is the balance point between all these data points? Now we know from before that the average was 3, so let's use that and look at 3 as our average or our mean. And to find the average, I would still use that same formula, that same reasoning that we used before. We're going to use the idea of distance from the mean or the balance point as a way to think about the data in more complex ways. So we're looking at these data, we see that one of these is 1 away, that was lion. Fox is 1 away. And sloth was 2 data points away. And if you're familiar with a seesaw, if you sit twice as far away, you pull the seesaw down twice as much. And that's just sort of a physics property about how distance relates to the weight. And here we're treating all the animals as though they weigh the same. So they all have the same pull as long as we take into account their distance from the middle or from the balance point of the seesaw. And then we had gecko was 1 away on the other side, and owl was 3 away on the other side. And so this is a little messy with all these lines everywhere. So to simplify it, I'm going to put these values, this 1, I'm just going to put it inside the circle. So the number inside the circle is how far away it is from the mean. This point is how many books were actually read. So if you read 2 books, you're 1 away from the mean. If you only read 1 book, you're 2 books away from the mean. So we can see then the total sort of pull on the left side is 4. The total distance altogether is 4. And the total distance on the right side is 4. And that's why 3 is the balance point for these data. So mean is balance point. This way of thinking about the mean is where we think of the mean as the point where the total distance on the left is the same as the total distance on the right. Those two distances are equal. All right. I want to use this to talk about spread. The range or spread or how spread out the variability in our data. We talked about this a little bit in class, but data are complex, especially if we have a really large set of data. We have a small set of data like the ones I've been sharing. We don't actually need to do a lot of data analysis to understand them. We can kind of just look at them and think about what's going on. I'm just using these small data sets to illustrate or demonstrate the formulas or reasoning behind how we analyze data. In reality, we really only need to do this kind of work when we have a larger data set. The data is so complex, we can't make sense of it. It's too many data points to look at, so we need to find a way to summarize it. One way we do that is with representations. We looked before in class at things like histograms and box plots. Another way we do it is with statistical measures. Things like measures of center, like mean, median, mode. And these are really asking kind of like what's typical for the data, or where's the middle of the data? What are they sort of centered around? It's a measure of the center of the data. And the others are measures of spread or variability. These are things like range and interquartile range, which we talked about with box plots before. And you don't need to teach standard deviation, but I know that many of you have heard of it. And there is something related to standard deviation that you are expected to teach that I'm about to talk about. These are really asking how the data are distributed and especially how spread out are they. We're interested not just sort of what's the middle of the data, but how consistent the data are how tightly clumped the data are around that middle. It's different to have a set of data that's really tightly clumped together than one that's really spread out. If we're thinking about, say, quality control or how well we're achieving our goals, we want to think about both of those things when we're looking at sets of data. Summarizing the data always simplifies it. That's the point of it. It's so complex, we need a way to look at a sort of a simpler piece of it. So we lose some detail. All of our ways of representing data, whether it's a visual representation or one of these statistical measures, we're losing some detail. And they highlight certain features and make them stand out to us. That's the reason we do them, but it's just something to be aware of when we're summarizing data. All right, so let's go back to our animal book club. And we're going to think about how the mean as a balance point can help us reason about how spread out the data are. And to do that, I want to compare to a different book club. And in this book club, we have 3 animals that read 3 books each, and 1 animal that read half a book, they got halfway through and stopped, and another animal that read 5.5 books. And hopefully we can see here visually still that 3 would still be the balance point. All those ones on the middle won't really affect which way the seesaw goes, and the other ones are both the same distance apart. And to show those distances, we can see these ones are all 0 distance away from the average right here, and the ones on either side are both 2.5 books away from the average. Now, one way to look at the spread of data is to look at the range, the difference between the maximum and the minimum values. And on both of these, that's 5, right? If I go from 5.5 to 1/2, that's a distance of 5. If I go from 1 to 6, that's a distance of 5. However, the top data set feels much more compact. It looks more compact. Yes, we have the same spread between the 2 extremes, but in the middle of it, we have a bunch of data clustered. And again, I'm using really small data sets to illustrate the concepts, but with a much larger data set, if we had, a few data points over here and a few over here, and then a whole bunch of data points in the middle here, that would feel much more compact than one where it was like pretty evenly spread out across that. So we're going to think about how we can use this distance, this balance point idea, and the distance from the middle as a way of thinking about how spread out the data are. If we look at this top set of data, the overall distance, how far away are things from the middle or from the average, is 2.5, sorry, this goes with this 2.5, 0, 0, 0, and 2.5. So altogether, we have a total distance from the mean of 5. And then that's spread out, or that's over 5 data points. So we divide that by 5, we get an average distance of 1 from the middle point here. And on the bottom set of data, we have distance of 2, 1, 1, 1, and then 3. So we have a total distance of 8. Again, that's over 5 data points. So we divide by 5 and get an average distance of 1.6 away from the middle. And you might be asking, well, why do we have to find, oops, I apologize. Why do we have to divide by 5? Can't we just compare the 5? This is much smaller number than the 8 instead of comparing the 1 to the 1.6. And the reason for that is we want to account for if we have 2 different size data sets, we want to be able to make a fair comparison across them. So let's look at this. I kept this data on the bottom the same, but on the top, I have another book club where a ton of animals read 3 books, a bunch read 2, and a bunch read 4 books. Here, I'd have my total distance would be 5 times 1, 1, 2, 3, 4, 5, plus 0, and then another 5 on this side. I'd have a total distance of 10 away from the middle. And here I'd still have my same distance of 8. So 10 is bigger than 8, but this data set is much more compact. It has less spread, less variability. So that's why we want to divide by the number of data points. The only reason this number is higher is just because there were so many more data points. And so this one is actually less than half the spread of this one when we measure it in this way. I do want to clarify a little bit about the language here. The word absolute deviation is the fact that I'm counting these as positive distances, 1, and these as positive distances as 1. I don't care if it's to the right or left. I treat it as the absolute value as a positive distance either way. Mean doesn't refer to 3 as the mean. It's referring to the fact that I find all my distances and then I find the average distance away. I divide by the number of data points. So it's the mean distance away, the average distance away. That's just where that language comes from. All right, so that's a second way of thinking about it. And again, you don't have to teach standard deviation, but I do want to talk about how mean absolute deviation relates to standard deviation. Mean absolute deviation is a really powerful way to think about spread in and of itself, but it's also an important foundation that could be built on in higher grades. All right, so just in terms of thinking about a calculation or a formula for how you find this, what are we doing? We're looking at our data point 6. This is the mean absolute deviation still. We're looking at 6 minus the mean. We're looking at each of our data points, the distance to the mean. 6 minus 3 is 3. 4 minus 3 is 1. However, when we get to this side, we would have a negative value. If we take our data point minus the mean, we'd end up with a negative value. And therefore, instead, we just use absolute value. And again, that's where that absolute comes in the name of this. And when we do that to these other 2 data points over here, that's not a problem. It doesn't change their value. But as we continue on the other side, it'll keep our values positive. And then we're adding up the total of these and dividing. The standard deviation has a different way of dealing with this negative problem. This is a really powerful measure, like I said, on its own. However, algebraically, so both in terms of computing and doing computations, but also in terms of doing more advanced mathematics with it, the absolute value function is sort of a little hard to use algebraically. So instead, the standard deviation uses a different approach. We look at this distance again, 6 minus 3 is 3. However, then what we do is we square it. So we imagine the square here, and we're really looking at the area of this square, so we get a value of 9. And this is positive, and this stays positive, so that's fine. But as we get to, and same with this one, it remains positive, as we get to negative values, we have a negative one, but when we square that, we get a positive value. And so that's a different way of dealing with the fact that we get negatives versus positives. And over here, we'd have an area of 4. I'm going to move this up here so I can do a little more math. Just like with the mean absolute deviation, we're adding these all up to find the total area of all those squares. And then we are dividing by the number of data points to average it out. And we get 3.2. And that's not quite the standard deviation. We call that the variance. And then we take the square root. And the reason we take the square root is because these were areas. And we're not really interested in area. We're interested in length or number of books, the distance away. So we take the square root to get back into the same units that we were originally in. And so that gives us a standard deviation of 1.79. So it's very similar. It's just that instead of doing absolute value, we're squaring everything to get it positive, and then we're taking the square root at the end to get back into our original units. And again, it's not something that you need to teach standard deviation, but I do want you to have a sense of how mean absolute deviation, which which is in the standards, and you are expected to teach, is foundational or something that could be built on in more advanced grades or in higher grades. Now, one thing some of you said you did know, although I don't know if you could have recreated this picture in the moment, but that you had seen something like this or learned something about standard deviation like this. And so there's a lot in this picture, and I'm going to talk a little bit about where this picture comes from, and I'll come back and explain it. So one thing we might do when we're looking at a data set, is we might look at an individual piece of data and think, okay, how far away is it from the mean? And of course, we know it's 1, 2, 3 away. But that's like the absolute difference. It's just the number of books. But we want to have a sense relative to the overall data set. And since our mean deviation is 1.6, another way to say that is that this is a little bit less than 2 mean deviations away. If I jumped 1.6, I'd be about here. And another 1.6, I'd be around here. And so that's another way to think about how far away this data point is that it's about 2 of these away. Then, and so we can do the same thing with the standard deviation. We can measure how far away we are in terms of number of standard deviations. So that graphic, which I'll put up again, is really centered around the mean. So this 0 is saying we're 0 away from the mean. So this is the mean of our data set. This is the average. It doesn't mean the actual value is 0. Now, this is really important that these numbers that you see on the screen only work when we have a bell curve. And bell curve isn't just any data that sort of goes up in the middle. There's a specific mathematical definition of a bell curve. And so these percentages we're seeing here, and I'm going to talk through what they mean, only work if your data fit that. Or sometimes we say, well, it's close to a bell curve, so we're going to approximate it with that. And so what we know is if we have data in that shape, or it's the normal distribution of the data, then if we go 1 standard deviation to the right and 1 standard deviation to the left, that will cover about 2/3 of our data. 2/3 of the data points will fit in there. And this is a nice smooth curve, so we're imagining lots and lots and lots of data points to make this nice smooth curve. And then if I were to go 2 standard deviations away on either side, I'd get up to about a little bit more than 95% of my data would fall within there. 3 standard deviations, I'd have really almost all of my data. I just have a teeny bit left on the tails. And that's something many of you have seen, I think. And I just wanted to talk through then where that came from, what that meant. And again, I want to highlight that only works if you have your data in a normal distribution. We can see in our data, again, 1.6, if I go 1.6 and another 1.6, I'm over here. And same thing on this side, I'd be over here. All of our data in this data set fall within 2 standard deviations. So that doesn't match the percentages we just saw. And most of the data sets you're likely to work with in middle school are not going to follow that distribution. And so I want you to think of standard deviation more along the lines of mean absolute deviation, where it's really a measure of kind of how far away the data points are on average. It's a slightly different way of finding it than finding the actual average distance, but it's pretty similar idea. And so I want you to think of that more than you think of that bell curve in terms of standard deviation. All right, so just to summarize, we talked about the mean as fair share, and that's really the foundational definition I want you to have in your mind. When you think of what mean or average is, it's as though you have the same total values, but you shared them evenly among all your data points. Then we also talked about the mean as balance point, and that's really powerful for thinking about the spread of the data, the variability in the data. We briefly mentioned range. We've talked about interquartile range before with box plots. And then we talked about how this balance point definition of mean can really help us think about this statistic called the mean absolute deviation, and then how that is related to standard deviation. So hopefully that's helpful in thinking about where these terms come from, what they mean, what the various formulas you've learned in school mean, and what they can kind of tell us about data. Please send me your math questions about this video or anything else at mathymatfk@gmail.com, or leave a comment on this video. And don't forget to like and subscribe.
Math's not a problem with mathematics.